Okay, so welcome back to the second module of the week 3. So we have been looking at the instruments. We've been looking at the analytical methods, the calibration curve, and how the data is collected, and all that. So in this particular segment, we will be looking at some of the instrument that is used to make to generate these data. So I'll look at some of these analytical instruments which goes into generating this data. So let's start reviewing them one by one. Again, I will not go in great detail about each and every instrument. Again, this course is on life cycle assessment. We are looking at these instruments just from the perspective of which instrument is used to collect what kind of data, since you should be aware of some of these aspects before you, if you're working with data, you should know where the data came from and how the data is generated. So just to have that aspects covered, I am giving you a very brief overview of the different instruments and how it is used. So we'll spend some time on maybe 5 or 6 instruments which are the common one. These are not the total exhaustive list of instruments. These are the common ones. We already saw one, the spectrophotometer, used a lot for doing a bunch of analysis in an environmental lab, whether you're talking about COD analysis or you're talking about even you can do like iron, you can do arsenic, you can do chromium. You can like a spectrophotometer has method for lots of analysis which you can do over there. The problem is when you have the colored sample, then it cannot be used. So let's look at some of the other more sophisticated instruments. So the number one is an ion exchange chromatograph. This is an older version of ion exchange chromatograph. The newer version looks much smaller. The thing in the middle is our which is known as the auto sampler. So here the computer is connected to the machine. Again, as you can see, these are the little bit older machine, and here you have your ion chromatograph IC, which runs on a it has a column either for ion for anion or for the cation, and the middle portion is your what is known as the auto sampler. So you can load the samples and the samples will be automatically analyzed, and there is a computer software which is connected to the machine. And so that, as I said earlier, the computer software is there these days to help you with the calibration curve and with the detection of different analytes present there. So what it is used for? It is used to analyze liquid samples for dissolved ionic or polar materials by charged property. So that's what it is used for. How it works? It has a column. The column, what it does is basically you at the very beginning you add a what is known as a packing material. Basically, you add a chemical in the column. So all the adsorption sites, all the sites where the different chemicals can go and get adsorbed to, or can, in a layman term, you think about that there is like a pipe or maybe a circular in a very crude way, if you can describe it. So you can think about there is a long hall in a circular. It looks like a circular shaped hall where people are. There are a bunch of chairs out there, and first we send a group of people to occupy all those chairs. So those chairs are signifying that binding sites, and then we add the sample in such a way so that the samples have these chloride, bromide, iodide, whatever, and this chloride, bromide, iodide has the more affinity for those binding sites, so it will kick those people out, kick those chemicals out which is already present there and occupies this space. At the end, you send a what is known as eluent. The eluent is the highest affinity for these binding sites, so the eluent will kick off all these different elements, different compounds that is present, or different anions or cations that is present. But since different anions have different kind of affinity towards that binding material, so first you will have the things which anions coming out which has the least affinity, then followed by the one which has like higher affinity than the least one, and it kind of goes up as your affinity goes from in ascending order. So then different ions will come out at different times, so that's what is known as the retention time. So ion exchange chromatograph is used a lot for essentially for anion, and it also used for cations. Anions such as chloride, bromide, sulfide, nitrate, nitrite, those things are your anions, and then cations would be your magnesium, sodium, potassium, and all those things are cations. With the use of ICP now, in most of the labs ICP is available, or ICP AES, or if any lab has an access to an ICP, people are not using this cation columns much in many of the labs. It's mostly just is now stick to anion column. So that's how it's being used. So that's the ion exchange chromatograph. Next, chromatograph, as I said, it's basically separating different fraction. Next, we have the gas chromatograph. The gas chromatograph is an instrument to separate complex gas or liquid. Although it is called gas chromatograph, it is a liquid can also be injected, but the liquid gets converted to gas before it is analyzed. Injected samples are separated in gas phase, which is the mobile phase, through the column. The separated components are detected by different kinds of detector. It could be a flame ionization detector, which is FID, or it could be TCD, which is a thermal conductivity detector, or ECD. There are different types of detector out there. So based on the analyte, different types of detectors are used. So here the gas chromatograph, very similar to the ion chromatograph. Again, chromatograph means separation of different chemicals. So you will have this different samples being carried through in the gas media, and in the gas media, while passing through the column, it gets separated into different fractions, different components, and the different components comes out at a different retention time. So that's how this the gas chromatograph works. Then you have a gas chromatograph mass spectrometer, which is known as GCMS. Here the difference between GCMS and the GC and a GCMS is usually GC comes with a detector, like a GCFID, a GCTCD, GCECD. But here our GC is coupled with the mass spectrometry at a detector. So what happens here is that in terms of GCFID or GCTCD, you already know what chemicals you are trying to measure. So you say if you have a soil sample, you want to measure pH. You have a water sample, you want to measure certain organic chemicals. So you already know what you are targeting. So you know at pretty much also you know at what based different methods you use, you can find out what would be the retention time for that particular analyte. But that may not be the case in for all the samples. Many times you have certain environmental samples for which you don't know. You have no idea of what is in there. So you have some guess, but you are not really sure what is in there. So for that, your MS actually helps. MS is like in mass spectrophotometry is like in a library, as comes with a library, where based on the mass and charge ratio, it looks at, okay, what could be the possible chances, what are this mass by charge ratio could be there for certain different types of chemicals. So based on that, it tells you that this chemical looks like this is this chemical, or look at maybe between it something around this particular line. So it helps you to pinpoint to what chemical it could potentially be there, and then for that particular chemical you can go back and run it again on GCMS, or you can run it on GCFID, TCD based on what kind of chemical it is and what kind of detector is used for that. So that's the benefit of having a GCMS. It helps you in terms of the identification of the different components. Then HPLC, very similar to IC, but very similar to your IC, but here HPLC is used to separate complex chemical into single components. Here the mobile phase is liquid, because high performance liquid chromatograph. So mobile phase is a liquid, and the separated components can be detected by UV vis absorbance detector. Since an HPLC can only handle water, more complex and greater molecular weight chemicals can be analyzed. So HPLC is mostly just to use as you use it for the liquid sample. So you can do many complex and greater molecular weight chemicals. Many times you have pharmaceuticals, personal care product, those things are used using an HPLC. Similar to GCMS, we have LCMS, which is a liquid chromatograph mass spectrometer. Again, mass spectrometer, same procedure, same concept, and liquid. It's used for looking for large molecules such as pharmaceutical products and proteins and whatnot. So those are used to analyze for these chemicals out there. Then ICP, which is very popular for heavy metals and for inorganics. Again, this particular ICP that you see over here, it's a pretty big machine, but if you look at the newer machine, they are becoming much smaller. There are now benchtop like ICP MS available as well, but some of the older machines were pretty big. So as you can see it over here. So this is a computer which is controlling the machine. That's the machine right over here. Several electrical stuff, as you can was there. That's your argon gas cylinder which supplies gas. This is where the plasma chamber is, where things. This is where the torch is, and this is where actually the plasma chamber, where things gets like a through the nebulizer. The sample is, and there is a auto sampler which is kind of over here. You cannot really see very well, but it's between the computer and the machine, the main part of the machine. There is an auto sampler, and we have this samples injected into through and like a nebulizer over here into this chamber, and there we have your things getting like excited. So how the concept of ICP AES is as you probably know, ICP works at very high temperature, 5,000 to 10,000 degrees centigrade. So the concept of this ICP AES is that you have this sample, you atomize it, you take it. If you remember your modern physics, the Rutherford model, you take your atoms present in those samples at a higher excitation state, and then you let it go down in a lower excitation state. And when it goes down to the lower excitation state, it releases energy, and that energy, if you remember, E is equal to hc upon lambda, and the lambda is the wavelength. The wavelength for each element is unique. Different elements have different wavelength. So for that matter, your E hc upon lambda, c is the speed of light, h is the Planck's constant. So since lambda is unique to a certain element, so based on the emission light that is coming out, if you know the wavelength of that light, you can relate it to what element it belongs to, whether it belongs to sodium, whether it belongs to potassium, whether it belongs to arsenic, whether it belongs to lead. And so based on that, you can always predict which element is present at a higher concentration. So again, as you saw in the previous module, there will be a calibration curve involved here. So you will run a calibration curve, and calibration curve will be prepared. These days software does the job for you. Many times you don't realize what was got done. So you have the calibration curve prepared, and then you run your samples. You need to have your calibration check samples in between. The machine gets like heated up. Typically what I have seen based on my practice is when you run around 100 to 150 samples, and after that you may have to go back and recalibrate, because the calibration goes off as the machine gets heated up. Either you stop for that particular day or you come back. Most of the typical ICP-MS or ICP-AES, they take 3 to 4 minutes a sample. So if you start it early in the morning and run it throughout the day with maybe one or two calibrations in between, you can end up analyzing around 300 to 400 samples per day. So that's a pretty good like a throughput for an ICP-AES. So like 400 samples, if you look at 3 minutes a sample, so around 1200 minutes. So 1200 minutes is around 20 hours. So if you run it for throughout 20 some hours, so it's like a one-day work, you can run 400 samples. So that's not bad. One of the other is your atomic absorption spectrophotometer. Here works again, you are doing it for heavy metal. One advantage of doing ICP-MS or ICP-AES is that you can analyze for usually sometimes 26 to 27 elements at one time. The drawback, that's the drawback of atomic absorption spectrophotometer. Here we use we can do only one sample at a time. So if you have to look at several analytes, then it becomes a very time consuming. For each sample, each analyte, you run the sample, then you find out the data, then you change the lamp and do it for another sample. So that's why it becomes a more time consuming as opposed to doing everything together as we do it in ICP. So these days with ICP-AES or ICP-MS becoming more affordable as compared to earlier days, so you don't see many labs trying to use AA that much. They potentially go for ICP most of the time. There are some matrices for some elements in which ICP doesn't work very well, so we'll like to go and run graphite furnace atomic absorption method to do those kind of analysis. So that's how we get all these different, so these instruments which are used to get the data. And so this, so far, if you look at what we have covered in this module and the module before, we were looking at the environmental data, how the data is collected. We looked at the calibration curve, we looked at the method detection limit. We also looked at what we need to be careful in terms of the calibration curve, what we need to be careful in terms of the detection limit. If the machine will give you a number, but you need to make sure the number is correct. Then at the same time, you have to understand, have a broad understanding of how this different machine works. You may not have we don't expect you to have a very thorough understanding of how each of these machine works, but at least have a broad understanding, the basic principle at which these environmental instruments are working, because so that you can defend your data, or if there is a problem with the data, you can try to find out where the problem could be, because if you are aware of the methodology, at least in I may not have a great detail, but at least in terms of big picture, you should have an idea how the particular technology works. So technology for the instruments works. So in terms of data, once the data is collected, many times we may have to do some statistical calculation. Statistical calculations are needed while working with concentration. So the concentrations results are often directly used as part of regulatory decision making. So for example, if it's a hazardous waste or whether it could be land applied, it is necessary to perform a statistical analysis. So we do for the hazardous waste, for example, you do a TCLP test, which we'll talk about that in a minute. So if you want to find out whether a waste is a hazardous waste or not, we do certain tests out there. Or if you want to find out whether certain things is safe, for example, the biosolids is safe to be land applied, we test that biosolids and to find out whether it could be land applied or not. So that decision is based on the data. Now, if the data has to be good, and the data has to be statistically tested as well. So we do a lot of statistics on it. And again, if you go back to your statistics class, remember that population mean and the sample mean. So for any environmental sample, say for example, you have gone to a contaminated site, and it's a contaminated soil. Now this contaminated soil, it needs to be treated, or you want to find out what is the real concentration level. So for that, you have to collect what is known as the representative sample. Now how will you know what is the representative sample? More the heterogeneity, better the higher the number of sample, better it is for heterogeneity. If it's a homogeneous mix, you don't have to, it becomes easier. So for the water, to certain extent wastewater, you may probably don't need too many samples for that particular water. Like we try to have at least 3, because that helps us to get the standard deviation and do a little bit of statistics, even basic statistics on that. But you don't need more than 3 for water or wastewater sample, for that matter even air sample if it's a nice well mixed system. But if you talk about soil system or solid waste or hazardous waste, where there could be a lot of heterogeneity, municipal solid waste, it's a lot of heterogeneity. Like if you look at just the 2 garbage pile, although they may look the same, but if you look at more carefully, if you, as a layman, it may look the same, but if you look at very carefully as an environmental engineer, you will find that there are differences in there. Some may have more plastic, some may have less plastic, means difference in calorific value. And same thing, some may have more biodegradable matter than the other. That means the other one is probably not good for anaerobic digestion. We need like a biological biodegradable material present for the anaerobic digestion. So those kind of things we can make the decision as an engineer when we look at some of this stuff. So, and we do have to do statistics on that. So to say for the contaminated soil sample or the solid waste sample, you go there, you have a pile of soil. Now how to collect the representative sample from here? You can collect 1, 2, 3, 4, but is that enough? If it's again, if it's nice mixed soil, maybe that could be enough. But if it's a heterogeneous mix, as we have mostly in the waste management side, it may not be enough. So the site concentration results are often directly used as part of regulatory decision making. Is this a hazardous waste? Is it land applied? So it is necessary to perform a statistical analysis, so that whatever is the sample mean or the sample information you collected, that can be extrapolated to the population level. So that's how we talk about the sample and the population. So what is the chemical concentration of a waste? Very rarely the waste or the contaminated soil is completely homogeneous. If you look or think about the waste, in terms of water, probably it's better, but in terms of waste, you don't see, very rarely you will see waste or contaminated soils completely homogeneous with respect to chemical concentration. So what we need to do is we must collect and analyze multiple samples to determine what some representative concentration is. We need to do some multiple samples, do some collection of the multiple samples. The more the heterogeneous the matrix, the more samples may be needed to accurately describe the representative concentration. So as you can see in the last bullet, more the heterogeneity, more number of samples are required. So that's again very, very careful. Now what is the representative concentration? Representative in terms of the statistics, there are some estimates of the central tendency. We talk about the mean, which is the average, median, which is the middle number, the mode, which is the most common number. Then there are some upper and lower confidence limit as well, which is also used in terms of statistical analysis. And some things you need to consider is the sample distribution, what kind of sample distribution we have, what the data will be used for, what is the use of the data, what it will be used in terms of implementation, or in terms of just a general design. So based on the data requirement, what kind of data, how detailed the data is required, we can decide in terms of what we need to do in terms of statistical analysis. But some of the things that we definitely need to consider is what is the sample distribution. As you can see, in terms of representative concentration, we need to find out, okay, what is the sample distribution, whether it's a normal distribution, log normal distribution, and we'll talk about that, how to find that, and what the data will be used for. So these are some of the information that you need to know in terms of the collection of the data. So in terms of sample distribution, if you look at this particular graph here, two sets of two graphs. So here we have first one on the left hand side. This is the normal distribution, very common. You may have seen it, and it's a classical like a statistical distribution. And then on the left hand side, on the right hand side, what you see is a log normal distribution. So this is the log normal distribution, and this is the normal distribution. So the log normal distribution is typically what we see in the environmental sample. We don't see that much of a normal distribution. So normal distribution, we'll talk about that in a minute. So if you look at some of the examples, say if you have a type of data, type of distribution dictates how you calculate the central tendency. So it depends on what kind of the type of distribution does have an impact on how to calculate the central tendency. Now let's look at some example. This is one example where we have the data. Say this is was done on some TCLP test. TCLP stands for toxicity characteristic leaching procedure. I haven't defined this test so far. For your class here, you can just think about that this is a test done on soil, sediments, solid waste to find out whether that particular waste is a hazardous waste or not. So this is just like a citric acid and EDTA solution which is mixed up together. So we have the TCLP is what you're trying to predict what will happen in a municipal solid waste landfill. So you will have this acetic acid and sodium hydroxide, which is mixed together to make the TCLP solution. And then you take 100 grams of samples and 2 liters of the TCLP solution. You run the extraction, and after one day, 18 hours, you have the concentration. And the data here shows concentration for 29 samples. As you can see on that data, if you look at carefully, here we are varying from data of 1 to the maximum. The minimum value is 1 and the maximum value is 9. So there is quite a variability in the data set, which I was trying to explain earlier, that environmental data at many times it's a heterogeneous sample. So in a heterogeneous sample, you will see these kind of variability, and with n is equal to 29. So you plot it. You plot this data, and then you see that there is a arithmetic. You find the arithmetic mean 4.83, median is 5, mode is 5, and this one is a classical distribution that you see. This resulting histogram is a similar shape as a normal distribution. As you can see from the graph, the mean appears to be a good estimate of the central tendency. So this is so you can think about like a nice classical shape graph, and with the arithmetic mean, modium and mode and is present there. So this is if it's a like a arithmetic mean. So now if you have a data set, if you would consider a different data set again for some TCLP results where you found the results varying from 1 to 20, so like a lot of variability, n is 31 number of samples, you plot that data, you see a like a long tail. So long tail usually means log normal. So that's what it means, that it is a log normal distribution, and here you see arithmetic mean of 5.32, median is 4 and mode is 3. So this is another example, and what we will do is in our next module we'll kind of continue this distribution further. So you will have to remember these two data points for your next module, but you will always have the access to the PDF file, so you can look at that up as well. So far what we have learned in this particular module for last 30 some minutes, we started with looking at in terms of different instruments, what are the different instruments out there. Those are again not the total exhaustive list of the instrument, these are some of the common instrument available in the Indian labs. So that's what the instrument was and how each of the instrument works, kind of got some idea on that. Then we also looked at some of the statistical aspect associated with environmental analysis, how this statistics play a role, and then when you look at this distribution of the data, like a normal distribution, log normal distribution, what are they mean. So we had some examples of that. So with this we'll like wrap up this particular module, and then we will look at the next module, which will be your module number 3 of week 3. And then we'll continue this particular discussion on this TCLP data and the statistical analysis, because we have some statistical data to show there as well. So okay, so that's let's kind of wrap it up for this particular module, and then again I'll see you in the next module. Thank you.